Okay, let's start. So, today we are going to look at some problems based on propositional logic, very basic problems essentially. So, the first problem is, if L is countable, then SL is countably infinite. What's the answer? How do you show that? Bounded above using
strings and bounded below using L.
bounded below using
Like L.
L. Okay, yeah. I mean, well, I should say is non-empty. Yeah, that thing needs to be added. Yes, so we need to show that this is countably infinite. So it is bounded below. So suppose P belongs to L, then negation P, negation of negation P, negation of negation P, and so on. They are elements of our L formulas. So how many are there like this? There are countably infinitely many such formulas, right? So therefore Aleph naught is a lower bound for SL okay, because these are all formulas, they are all distinct. Yes. So therefore this is a lower bound, and upper bound, for the upper bound you have to notice that every formula is a finite string of symbols. Yes, so which symbols can we use? Anything in L, and what other symbols can we use? Conjunction, negation, and parenthesis. So any L formula is a finite string as in like we are writing a word or string, finite string of symbols from L, and these symbols. So if L is countable, then what can you say about this set? That is also countable. Yeah, so which is a countable set? Therefore, SL is contained inside the set of finite strings with countable alphabet. See, I am saying contained. Is it equal? Can it be equal? Can I just write open parenthesis? Is that a formula? No. So therefore it is contained, properly contained. But finite strings with countable alphabet, how can you write that set? We can write it as a countable union of strings of length n, where n varies. Correct? So let An denote the set of length n strings with alphabet L union okay, this one you know. So what can you say about the cardinality of AN? Come on. AN is countable. AN is countable. How? For each place we can choose one symbol from A. So therefore AN is actually a finite power, the power n. This language cross, I mean this alphabet cross alphabet taken n times. So therefore AN is, since finite product you all should be prepared for the exam and instead you are not saying anything. This is something we did in week 2. Yeah, since finite product of countable sets is countable, AN is countable and hence so is union of AN, n belongs to omega, correct? I mean if we need we can use axiom of choice, yeah, countable axiom of choice, and this union AN is precisely the right hand side here. So therefore we are done. So we showed that aleph naught is a lower bound, aleph naught is an upper bound, and therefore we get what we need. Any questions? This is perhaps the simplest possible question. Let's go to the next question. Suppose S is an L formula and let LS and RS denote the number of left and right parentheses in S. Then can you show that LS is equal to RS? What kind of formulas are there? There are 3 different types of formulas. The first formula is a propositional variable. How many left brackets are there in a propositional variable? 0. And for right bracket, so LS is equal to RS. What is the other form? Yeah, so every formula, let me write that. Each S in SL is of one of the following forms. One of the 3 forms. The first one is that S belongs to L and here LS is equal to 0 is equal to RS. Second, S is equal to negation T. Then what can we say? I mean, what kind of proof should we use?
Induction.
Proof by induction, very good. So S is equal to this. I mean, let's say this is our base case. Yeah, maybe I should change the order. I should say that this is my base case. And then inductive case, one of the 3 forms. So here I will write, we will use induction on N. What is N here? Induction on N. So S belongs to S0L, that is what we were doing earlier. So here belongs to Sn plus 1L, and we wanted where T belongs to SNL. So what can you say about T? The number of left parentheses in T. So then L of S is equal to 1 plus L of T, but L of T is equal to, so this is by induction hypothesis, this is equal to 1 plus R of T, and this is equal to R of S. Similarly, so inductive case has two steps. S is equal to T conjunction U, where T and U are in SNL, so the result holds, and then L of S is equal to 1 plus L of T plus L of U, correct? So this is equal to, by induction hypothesis, 1 plus R of T plus R of U is equal to R of S. So we are done. Very simple and boring proof, but let us see if you can use the same logic over here. Suppose W is a non-empty proper left subword of a propositional formula. Non-empty proper left subword. So basically, I will give you an example first. Suppose I am writing this. Then I can have this word just one parenthesis, then I can have this word two parentheses, 3, 4, yeah, any of those left subwords. And what do we need to show? That L of W is bigger than R of W. What is our method of proof? Induction. There can't be anything else. So once again there is base case. Yeah, I will perhaps not write the entire proof, you can formalize it. The base case is that S belongs to S0L. Then can there exist a non-empty proper left subword? It just has length 1. Yeah, so either the subword is empty or it is everything. So there is nothing to prove here. Yeah, so base case, nothing to prove. Then what about the inductive case? In inductive case, you can either have S is equal to negation T or you can have S is equal to this. So let us consider this case. Okay, then what will happen if, yeah, I am just going to write this. If S is equal to negation T, then non-empty proper left subword of S has one of the following forms. Well, it can be just this parenthesis. It can be that parenthesis followed by negation, or it can be T prime. Yeah, sorry, maybe I should call it W dash, where W dash is a left subword of T, or finally it can be just this. Okay, these are the only possible 4 forms. Now, what will you do in the first case? If it is just a parenthesis, then how many left parentheses are there? 1, right, 0. Second one also same, 1 and 0. Third one, what will you do? If it is a proper left subword of T, W dash is a proper left subword of T, then by induction hypothesis you already know that L of W dash is bigger than R of W dash, and then what is L of W? 1 plus L of W dash, and therefore you can prove the result. And in the last case, well, T is a formula. So therefore L of T and R of T are equal, and therefore 1 plus L of T is equal to L of S, and that is strictly greater than R of T. Done? Okay, can you do the second part as well? If S is equal to T conjunction U, then what are the forms? Either it can be just this parenthesis, like open parenthesis, or it can be open parenthesis followed by some subword, left subword of T, in which case we know what to do. Then, or it can include an entire T and then just this, in which case also this open parenthesis is extra, or it can contain some left subword of U. It can go until some left subword of U, in which case you can use the result for U, induction hypothesis for U. Yeah, so this is again very boring and straightforward proof. I am not going to finish this. However, we need this result. The result is interesting, but the proof is boring. That's what I am saying. We need this result to prove the unique readability theorem. So, we know that every single formula can be written as one of the three forms. Either it is in the language, or it is negation of something, or it is conjunction of two formulas. The question is, can we write a single formula using two such different forms? Any ideas on how to prove this? If I say that the length is 1, length of this formula is 1, then what can it be? It only can be propositional variable, and that propositional variable is uniquely determined. So without loss we can assume that the length is bigger than 1, which means we have taken care of S0 basically. Okay. Now the question is, can it be of form 2 and form 3 simultaneously? Can it be of form 2 and form 3 simultaneously?
So can we do it by counting the left brackets and the right brackets?
Yes, if necessary. Do you have any idea in mind how to count and then prove it?
So for the second form it would be only the left bracket of T, but for the third form it would be L of T plus L of T.
L of T plus?
L of V plus 2 plus 1, and for the second one it would be 1 plus L.
And on which subword are you applying that? You had to tell me which subword is that.
So the whole formula.
The whole formula. The whole formula L is always equal. L and R are equal in both these cases, right? We proved that. Even if it is of second form or third form, it doesn't matter. L and R are always going to be equal.
So but if they are the same, then L of one should be equal to L of the other.
Yes, L of one should be equal to L of the other.
There can we prove it? If V
And how will you prove that? That's what my question is.
if V is not a propositional variable, then we would have at least one.
Do you mean U? U is not a proposition.
U is not. Then it will have at least one bracket.
We don't have to go that way. Just look at the strings, how they start. Okay. So, what can T be? In formula 3, what can T be? t can either be a propositional variable or a formula which is not a variable. So, either t can be a variable or the first syllable, the first letter in t can be a parenthesis or a propositional variable. Whereas, look at form 2. In form 2, what is the second letter? It's negation. So, therefore, they can never be equal to each other. Yeah. So, it is enough to argue when S is not in L. If S is equal to negation T for some T, or perhaps I will make a slight change. Yeah, we are facing problems because I am using the same notation over here. I am going to convert this into U1 and U2. Okay. If S is equal to negation T for some T in SL, then the second syllable, second letter is negation. However, if S is equal to U1 conjunction U2, then the second syllable or letter, syllable and letter are the same thing. We will use syllable very properly next time. So, maybe I should use letter. Second letter is either an open parenthesis or a propositional variable. Therefore, no formula, no L formula can be written as both form 2 and form 3, because their strings are different, the second symbol is different. Okay. Now, yes?
Like suppose U1 is also negation of something. And
even if it is negation, after negation we put a parenthesis. So, don't forget that.
Yeah, but that will be, then the third letter will be negation.
Third letter will be negation, but the second letter in that case will always be open parenthesis. Whereas, in that negation, in second form, it will be negation. So, therefore, they are going to be different. Any other questions? Yes?
Sir, is it necessary for every formula to have a unique string?
I mean, you just don't want to solve this question. So, I mean, all of you know coding. Yeah? So, in coding, don't you have to be precise, otherwise there are bugs? So, why does a code work? Because it has unique readability. Whatever you write should have a unique meaning. If you mess up one symbol, will it accept your program? Will it run? No. So, you can be precise there, then why are you asking why? I mean, this is the logic behind coding.
But we can't put as many brackets as we think.
You can put as many brackets.
Because
Even in coding, can you put as few brackets as possible? Yeah, I mean, if you miss out on some parenthesis, will your code still work? Parenthesis, curly brackets, square brackets, whatever you are doing, if you mess them up, then it doesn't work. One of the rules of coding is also what we wrote here. The left and right parenthesis should always match.
No, the number matches, but
The number matches, but the number can vary.
yeah.
Yes, the number can vary, but it again has unique readability. So, there are rules like what binds closer. We also had those rules. Yeah, that negation binds closer than conjunction and disjunction, which themselves bind closer than implication and by implication. So, there are some rules. Yeah, but they are taught to a machine. Yeah, it's not automatic. Everything has to be taught. Computer programming works on the principle of Turing machine. Yeah, it only reads one symbol at a time. So that string of symbols, every program is a finite string of symbols. So that string of symbols must be uniquely readable. Similarly, in logic also, if we are doing something formally, then it should be uniquely readable. And in fact, yesterday we showed an application. Do you have any other question? Are you happy with this? Okay. So, okay. So, no L formula can be written as form 2 and form 3 both. That much is clear. Now, if I have two formulas of, the same formula, can it be written in two different ways using form 2? So, the next question is, if S is equal to negation T and S is equal to negation T dash for T and T dash in SL, then can you conclude that T is equal to T dash?
Logically equivalent.
No, not logically equivalent. There is no logical equivalence here yet. Yeah, we are talking about plain syntax. See, how do you recover T from this S? You remove the first two and you remove the last letter. Then you can obtain T. Similarly, if you remove the first two and last letter, then you can obtain T prime. Then clearly, T is equal to T prime. So, there is no question whatsoever. Okay. So, therefore, there is no problem here. However, we need to do some work. If S is equal to U1 conjunction U2 and S is equal to U1 dash conjunction U2 dash for U1, U2, U1 dash, U2 dash in SL, then we have to do some work. Yes, so first we said that, it was propositional variable just length 1, so there is nothing to check. It can only be of form 1. Then we showed that 2 and 3 simultaneously cannot occur. Then we said that 2 and 2 cannot occur simultaneously. Now only remaining case is 3 and 3. Now what will happen in this case? Well, if U1 and U1 dash are equal, then we are done. Yeah, so if they are not equal, then what will happen? I am going to write this string. Yeah, so this is U1. So without loss, we can assume that this is the length. Yeah, if U1 is not equal to U1 dash, then without loss of generality, assume that U1 is a proper left subword of U1 dash. I am beginning to read in two different ways. Yeah. So the first way is that I start with U1 and then I hit this conjunction symbol. But now there is another way where I have to go a bit further to hit the conjunction symbol. Then without loss of generality, one of them has smaller length, because we are talking about length. Length is in integers and it's a linear order. So trichotomy, yeah, we are using trichotomy here. So if U1 is a proper left subword of U1 dash, and U1 is of course a formula, so it is non-empty. So then what will happen? U1 dash is a formula and it is a proper left subword. So therefore, the number of left parentheses in U1 has to be greater than number of right parentheses, which is a contradiction. A contradiction to U1 in SL. Because if U1 is a formula, then the number of left and right parentheses must be equal.
Sir,
Yes.
why we are assuming here U1 to be a subword of U1 prime?
Because it's the same string. Yeah, both of them are S.
No, sir, can't it be like that if A join B, A meet B, and something like C meet D,
Uh-huh.
where A and C are not same?
A and C are not same. Like, are you thinking of A and C as letters or they are formulas?
They are formulas only.
If they are formulas, then so either their lengths are equal or their lengths are different. If their lengths are equal, then we are done. Right? If their lengths are equal, then you go only that much length. The formula is still same. See, this is S, this is S. Formula is still same. So therefore, if the lengths are equal, then U1 is equal to U2. The next symbol is conjunction, and therefore U2 is also equal to U2 prime. U1 is equal to U1 prime and U2 is equal to U2 prime. So we are done. If their lengths are different, then what can you say? One of them is longer than the other.
So why is it so that U1 and U1 prime will contain in the same order, the things in the same order?
They are not necessarily. So I said without loss of generality. It can be that U1 is longer than U1 prime.
I'm not saying that. I'm saying that if U1 is composed of some statement, some formulas,
Uh-huh.
then why is it so that both of them will contain the formulas in the same order?
In the same order.
Yes, sir. Then only we will be able to say about.
What order are you talking about?
So it means the strings need to be same to some.
The string is, there is only one string. There is only one string, namely S.
Talking about U1 and U1 prime. U1 is a string.
U1 as a string. Can you give me an example?
So it means I'm just saying that what is the point of this proving this? We know that U1 and U1 prime will have the things in the same order to some extent.
To some extent, but exactly same extent. That's the point of proving this. Are all of you questioning why we need unique readability? Is that the point?
No, sir, the unique readability is sounding good, but this point, third problem.
See, let us take an example. So, negation P, conjunction negation Q. Is this good enough for you? Oh, maybe I'll take two things. Maybe I'll take conjunction Q, conjunction negation Q. This is a valid formula? Yes? So now can I write it in two different ways? What's your point now? Which one can be U1? What can be U1 prime? Negation P join Q, negation P conjunction Q is U1. Yeah, that's unique. But See, I cannot give you an example where u1 and u1 prime are different because that's what we are proving. It's not possible.
So what if we do negation Q and then conjunction negation, like we reverse U1?
Yes, okay, that's a good question. That if we are doing u1 conjunction u2 and then you do u2 conjunction u1, then they are different strings. We are not talking about formulas up to logical equivalence here. This conjunction is commutative up to logical equivalence, but it's not the same string. See, otherwise what's the point? Yeah, we said that P is a formula, P conjunction P is a formula, then P conjunction P is a formula, and there are infinitely many formulas. All of them, I mean, all but the first one is useless up to logical equivalence. But actually as strings of symbols, they are different. So therefore u1 conjunction u2 and u2 conjunction u1, even if they are logically equivalent, we think of them as the same, they are actually different. If u1 and u2 are different, then they are different. Yeah, so therefore we still need to prove this result. Any problems in the proof? Okay, then we have shown unique readability now. Let's go ahead. Okay, draw the Hasse diagram for this Boolean algebra. So how many atoms are there in this Boolean algebra? 4 atoms. So how many elements are there? 16. Can you tell me the atoms? Let us start with the bottommost element. What is it? Contradiction. Which contradiction should I choose? I should always talk about the class of a formula. Equivalence class of P conjunction negation P. Very good. Then tell me some atom. P conjunction Q is an atom. Okay, good. Any other atom? P conjunction negation Q. Okay. Then other atoms? Negation P conjunction Q and negation P conjunction negation Q. Okay, good. Now if we are allowed to use all the symbols, then can you tell me what is the top one? Contradiction. Top one is tautology. Huh. How to write tautology? P disjunction negation P. Okay. What are the coatoms? Coatoms are precisely the atoms of the inverted Boolean algebra. Negations of all of these? Yeah. Can you have some nice forms for them? P disjunction Q, yes. Okay, then P disjunction negation Q, yes. Then P disjunction negation P disjunction Q and negation P disjunction negation Q. Okay. So in the truth table for a contradiction, yeah, I mean it is a column. It is the column in the truth table. How many truths are there? 0. How many truths are there in the column for atoms? Yeah, so 1. How many for tautology? And how many for coatoms? 4 minus 1. Yeah. Okay. What are the middle formulas now? Okay, PQ. Then negation P, negation Q, P double implies Q, very good. negation P double implies Q. Okay, good. And then you can connect. Yeah, I am not going to do this networking. So there are precisely 2 truths in the column corresponding to all these formulas. And how many can there be? It's a column of length 4 and there are precisely 2 truths. So 4 choose 2, 6. So there are 6. So 1, 4, 6, 4, 1. Okay. I hope I don't have to teach you how to convert from one set of connectives to another set of connectives. If I ask you to write this P if and only if Q, yeah, I mean P by implication Q only using conjunction, you can write it. Only using disjunction and negation, you can write it. Yeah, I mean negation will always be there, but only using certain connectives that you can do. Any problems so far? Okay. Then let us look at some examples of logical equivalences and relations. So what about double negation P is logically equivalent to P? Is that true? How will you show that? Truth table. Okay, so perhaps this is simple. Truth tables you can all draw, but there are some interesting questions there. Yeah, so perhaps this you can do, but P disjunction negation P and R implies Q implies R. They are also logically equivalent. And yesterday I used a comment that there is no functional relation. Functionality just depends on this, that this contains P and this contains Q and R. So there is no cause and effect. What happens is that this is a tautology and that side is also a tautology. Because see, if R is false, then the whole implication is true. But if R is true, then Q implies R is also true. Because R is true, right? So therefore true implies true. So everything is true always. Yeah, it's very easy to check this. So therefore both of them are tautologies. Now we can ask similar questions. Yeah. So for example, if I write down some other formula, let's say I write down P disjunction Q and then I ask whether this equivalence class is less equal the class for P if and only if negation Q. If I ask this, how will you solve this problem? Implication? Yeah, I mean you take this formula, then you take implies the other formula and then you try to show that it is a tautology. If it is a tautology, then this less equal happens. And if it is not true, then the less equal relation does not hold. However, yeah, I mean, is there a quicker way of doing this? See, in general, I am asking you this, how to check this? If there exists, yeah. So, sorry, the answer is no. If there is a valuation V such that V of S is true, but V of T is false. So basically, when I am saying that this implies this is a tautology, what does that mean? That whenever the column in the truth table for this formula has T, then the same row in the column for this formula must have T. Yeah? If it doesn't happen, then there is some T here, but false there. In that case, we don't do anything. So you can solve all the problems related to this. Okay, I think the congruence relation question we have already done. And yesterday I tried to show this. Yeah, I mean in the atomless Boolean algebra case, I tried to show this. Maybe I should write on the next slide. So truth less than, so some non-contradiction formula was given, and then I was trying to show this. So this is given, that S is not a contradiction, so therefore this is less than. So because this is less than, we obtain some valuation for which Vs is true. Vs is true, and we needed to find something in between. And how did we find that something in between? If our language is countably infinite, then S being a finite string of symbols, it can only use finitely many propositional variables. So there is a new variable which does not appear in the formula S. And I choose that, I will call that variable P, and then I can put here, I can either put here S conjunction P, or I can put here S conjunction negation P. Now I know that there is a valuation V which makes S true. Now that valuation is either going to make P true or P false. If it makes P true, then S conjunction P is true. Okay, so S conjunction P is true, so therefore we have witnessed that S conjunction P is not a contradiction. Understood? On the other hand, if V makes P false, then S conjunction negation P is no. Oh sorry, S conjunction P is false. So therefore we have witnessed this less than. And then we construct another valuation which only differs from V in the value of P. And then you can simultaneously witness this or that. Yeah, so that's how you have to show both these less thans. Yeah, just showing one of them is not sufficient. Both have to be shown.